Hi everyone. In this lesson, I'm going to be showing you how to use Excel to do some modeling of experimental data. So this is totally fictitious, but let's pretend we had an experiment where we collected some bivariate data and I want to make a model. Now the model I'm going to try will be a power law. So y equals some constant k multiplied by x to some fixed power n. So the trick will be to find the appropriate number for k and for n that will be the best match to that data. So let's just set up a couple of little placeholders here where we could store the value of k and the value of n. And in these two cells, which I'll just highlight to make them stand out, are going to be where I put the numbers. Now I'd have no idea at the moment, so I'll just put k equals 1 and n equals 1 as a very, very rough guess. Now, what does that look like in my formula? Well, I'm going to try and write a formula that says k, so that's always going to be that number. Remember F4 to lock that, multiplied by x, that's the variable here, so no dollar signs, then to the power of the number n, and that one is a fixed number. Now, if it's a power of 1, it's a linear model or a direct proportion. So let's just copy those down. I don't expect them to be anywhere near correct. Probably won't do the last two. So those numbers are supposed to match those numbers. Now let's have a quick look at just the data we've got. So if we go from 0 to 6 to 12 to 18, we're stepping up by 6 every time. Now let's look at this one. 0 to 40 to 80 to about 120. So it looks like we're jumping up by 40 every time. It does look like this could be a direct proportion. So power of 1 is appropriate. Now the thing is, we're very bad as humans at comparing numbers in tables. So I'm going to make a scatter chart. Now the data points should be just the dots, and look at that. It is a beautiful straight line hitting the origin. I think direct proportion is correct. Now I'm going to add to this, so select data and then add. The x values will be the same and the y values will be my predictions. You can see they're nowhere near. Now I will format those to be a straight line. So we've done this before. We want a solid straight line. Let's make it orange and keep it a bit thinner. And when it comes to the markers, we don't want any markers. So the blue dots are the data points and the straight line is the model. The model is nowhere near good enough. Now, I'm happy with the fact that the power is 1 because that's what made it a direct proportion or a linear model, but k needs to improve a bit. So let's try 2. Not enough. Let's jump to 5. Close. Let's go to 7. Just a bit too much. Maybe 6.5. Just a bit under. So it's between 6.5 and 7. Let's try 6.7. And I don't think that's very bad. I think that's quite good. That orange line, which is my model, seems to be almost a perfect match for the blue data points. We can take a look down here. The data value and then the prediction. The model predicts 0. Model predicts 40.2 instead of 40, 80.4 instead of this. If anything, the 6.7 might be just a tad high. I can get a better handle on this by looking at a thing called a residual. A residual is literally the difference between the measurement and the prediction. So I'll just go that number there, subtract that one there. Of course, the first one hits 0, but we'll see what happens as we go along. Now, some of them are negatives and some of them are positives. That just means that the data point was above the prediction or below the prediction. A better way to compare these is to square the residuals. Squaring simply means they all become positive numbers. Now, I know in some sense squaring them changes them, but now they're all positive. So it doesn't matter whether the model was above or below. That's a measurement of how close the model was. If those numbers If the model was perfect, the residuals would be 0, and the squared residuals would be 0. So let's do the sum of all of these residuals. Now, sorry, I should have said the squared residuals. So that's the sum of the squared residuals. That's the sum of the squared residuals. That number there, 8.95, that's an indicator of how good our model is. The better our model, the smaller that number. Now we can get very fancy if we want to. I could use the solver application inside Excel. So I have an objective. The cell that I want to target is this one. Then I want to minimize it. And what do I want to change? I want to change the value of K. So make unconstrained values non-negative. I usually untick that. It seems to work better. And then I press solve. And it seems to have got a better answer. It's now down to 4.4. Mine was about 9 point something, wasn't it? So that's an improvement. And we've got a much finer detail here in the value of K. So the best model that I can find to predict or to fit this data is going to be y equals 6.675 multiplied by x to the power of 1. And that's how you do a power law model in Excel. Now, the good thing is once this is set up, then we can literally put any numbers we like into there and see how we go. Uh, I'll just pause for a sec. I hope I can pause for a sec and see if I can get a different set of numbers. Just let me see if I can. I don't think I've paused, have I? Okay, we're back on. So I've changed the numbers here, and you can see that my existing model, which is a linear model, doesn't do anywhere near as good a predictive job this time. So let's take a look and see what we can do. Well, again, start by examining the numbers. So the x values are going up in steps of 1, and the y values, well, we jump up by about roughly 5, then that one is about 20. So by doubling from 1 to 2, we've gone from 5 to 20. That's 4 times as much. That seems like a power law where the power is a 2, where it's squared. It's 4 times more. Double that, quadruple that. Let's try a triple. Oh, we can't do a triple. Let's go from 2 to 4. From 2 to 4 is a double. Now, this should be about 4 times. It is 20 to about 80. It seems like my power this time should be a 2. Already we're getting a lot closer, aren't we? Now let's see if I can do the solver again. Data, solver. It should still be pointing at the same cells. Let's just hit solve. And there's a very nice model. So it seems like this data is modeled. Now that's a terrible looking number. That's because we've got this one here where there was no data value. So we had a missing data value. We probably should take the model out of that one. So we're only looking at now. There we go. Our graph's got a gap in it, but I'm not looking for a final answer. I'm looking for a model. It looks like my formula would be y equals 4.84 by x squared for this one. So that's it. That's how you do modeling using a power law in Excel. Now, of course, the power n could also be negative numbers. It could be a -1 for an inverse relationship, or it could be -2 if you wanted an inverse squared law. All right, thanks for watching. See you next time.